Assalamu alaikum. Welcome to the lecture number 7 of Digital Signal Processing. Till last lecture, we have discussed the basics of digital signal processing and some basic signal models as well as manipulation of discrete time signals. Then we covered discrete time system and their properties in the live session. In this lecture, we are going to discuss how we can convert an analog signal into a digital signal. In this week, we are going to learn how to convert an analog signal into a digital form. As you all know that most of the real world signals are analog in nature. You can take example such as a speech signal. A speech signal is an analog signal. You can take example as a video signal. It is also an analog signal. Other examples are radar signals, seismic signals, and if you talk about your domain, which is biomedical engineering, so the biomedical signals are majorly analog in nature. If you say ECG waveform, it is an analog form. EEG waveform, again it is an analog form. Brain signal, again analog signals. So most of the signals in real world or the signals arises by the natural performance are analog in nature. So to study these signals or to manipulate these signals or to process these signals digitally, we need to convert these signals into digital form. So we have some criteria which will be followed in converting an analog signal into a digital signal. We will discuss these criteria and the statements and laws and the mathematical expressions governing this conversion. The main topics or the subtopics regarding this conversion which we will discuss in this lecture are written on the slide. We will discuss how we can convert an analog signal into a digital form, and in converting this signal, which rule is to be followed, which is the Nyquist rate, and what is the sampling of an analog signal. We have bit idea about the sampling when we discussed the continuous time signals and discrete time signals, but in this lecture we will see in detail which rules to be followed during the sampling procedure and how one can sample analog signal without any degradation in its quality. Then we will discuss aliasing effect, which will occur if we do not sample this signal correctly. After that, we will discuss the quantization. You have a bit idea of quantization process, as we have discussed the continuous valued signal and discrete valued signal in the first lecture. But here we will discuss it in more detail and under the perspective of analog to digital conversion. In quantization, we will discuss how we can quantize signal and what will be the possible errors arises due to this quantization and how we can limit these error to the minimum. Then we will discuss some definitions and the specifications regarding this whole process in terms of bitrate, file size and accuracy. So I hope it will be an interesting lecture, as analog to digital conversion is one of the most important domain of, or one of the main important area of digital signal processing. So coming to the first topic, which is analog to digital conversion. It means we want to convert our continuous time and continuous valued signal into discrete time and discrete valued signal. CTCV signal is an analog signal and DTDV signal is digital signal. So by this process, which is analog to digital conversion, we are actually converting CTCV signal into DTDV signal. And this discrete valued signal must have sufficient accuracy. The process is analog to digital conversion, and the equipment we used for this conversion is commonly known as analog to digital converters. So the steps we followed during this conversion is, first one is we will do sampling. The second step is the quantization, and the third step is the encoding of signal. You can also see from the block diagram that our input is an analog signal which is represented by XA of t. Since this signal is a continuous time signal, so that's why we used an index t in the parenthesis. This signal is fed to the first block of this block diagram, which is sampler, and this sampler basically samples this continuous time signal at discrete instants. That is, we are capturing the discrete or finite values for that continuous time signal which has infinite time values, or which exist for infinite time values. So the output of sampler is a discrete time signal. We will study this sampling in further detail in the next slide. But for understanding this block diagram, this sampler is just taking the pictures or samples of analog signal or continuous time signal at discrete values of times. So we will get x of n as the output of sampler. Then this discrete time signal, which is x of n, is applied to a quantizer block which will do quantization of this signal. And quantization is basically, or in general we can say, the conversion of continuous valued signal to a discrete valued signal. So at the output of this quantizer block, we will get an output signal named as quantized signal and denoted by xq of n. The error arises during this quantization process, or we can say the difference between the continuous value of the signal and the discrete value of the signal after the process of quantization is actually the quantization error, because both these signals will not be the same, as one is the input and the later one is the output. So the difference between the input signal and the output signal of this quantizer block is basically quantization error. Then after successful quantization of signal, this signal is applied to a coder block to perform the encoding of this signal, which is simply converting this discrete time and discrete valued signal into n number of bits binary sequence, because we want to process this signal digitally with the help of some processor. So we need an output in the form of some sequence, and preferably binary sequence. So this is the overall picture of analog to digital conversion, which involves sampling, then quantization, then encoding. The first two steps, which are sampling and quantization, can be performed in any order. That is, we can perform quantization first, and then we can do the sampling. But preferably and generally, the norm which is followed is to first sample this signal and then quantize it and then perform the encoding of that signal. So usually we prefer this sequence, which is first the sampling and quantization and then encoding. And by using this sequence, we can convert an analog signal into a digital form. But this conversion is not as simple as it looks like. There are various problems or issues which can arise in this conversion, and we can lose our data, which is very important or which may be very confidential or important. But by inappropriate conversion, we can lose the information and data will be useless after the conversion if we do not follow the standards and steps indicated for this conversion. So we will learn these standards and the criterias which needs to be followed during this conversion for lossless processing of the data. In this slide, you can see a plot which is representing how an analog signal is converted into a digital form. The original signal is basically an analog signal, and it is represented by dotted lines, which is then converted into a digital form represented by the solid line. So in this conversion process, you can see the original signal is somewhat different to the digital signal. That is, the exact values are not retained except few points. Otherwise, signals have some different values as compared to the original signal. So it means that sampling and quantization introduces loss of information, or we can say signal distortion. You can also verify this statement from this plot that both the analog signal or the original signal and the digital signal are perfectly not overlapping each other. So there is some loss of information. but we are more interested to retain as much information as we can. Here I am talking about the accuracy aspect of this conversion. We need to have a maximum accuracy of this entire conversion process so that we can extract the meaningful information from that digital signal if it is converted into digital form accurately. So the two steps, which are sampling and quantization, if we look at these two steps, then some loss of information encountered in these steps. In the first step, which is sampling, there might be some loss of information, or we can say signal distortion can occur in the sampling also. But if we choose correct sampling rate, then there is no such distortion in the signal, or there is no loss of information in this first step, which is sampling. So the criteria for correct sampling, or we can say if we want undistorted signal, so we need to select proper sampling rate. So proper sampling rate is the solution to avoid any distortion in the sampling step. And if we select inappropriate sampling rate, then a common problem arises, which is known as aliasing. We will discuss this aliasing in later slides in detail. But for here, it is clear that aliasing arises due to incorrect sampling rate. Now move to the second step, which is quantization. So if we talk about quantization, then quantization introduces distortion in signal for sure. We can't avoid signal distortion in this second step, which is quantization. So we can say that quantization is irreversible process. That is, once if the signal is quantized, then error is introduced in the signal, and by any means we can't get the original signal back if that quantization error will be introduced in that signal. So I hope you are getting my point, that in three steps, which are sampling, quantization and encoding, the first step may refer to no loss of information or no actual signal distortion. But If we talk about the second step, which is quantization, it is always an irreversible process, and it always introduces distortion in the signal. And this distortion, once introduced, can't be eliminated from the signal. So, as we are more interested to obtain more accurate signal, which is the accuracy aspect of this conversion, we need to introduce greater number of bits to ensure minimum quantization error. But on the other hand, if we increase the number of bits, which is the need of the second step, quantization, and the first step, which is sampling, demands us to increase the sampling rate as much as we can. But there is certain limit also. We will discuss it in the later slides. But for here, it is clear that to obtain an accurate signal, we need sufficient sampling rate, uh, referred to the first step, and we need higher number of bits for the second step, which is quantization. So these two we can say these solutions of these two problems result in increased cost of that converter. So we have to trade off between the accuracy and the cost of the converter. If we want a higher accuracy of the converter, then it must be costly, because in that converter there must be higher sampling rate and there must be greater number of bits. But it also depends upon the application area or the nature of signal which we want to process, that how sophisticated the signal is, the actual information is, then we are able to select the proper analog to digital converter, which will provide us the digital signal with sufficient accuracy. I hope you are getting my point. So these 2 points, which are sampling and quantization, we need to look at these points in much detail for our better understanding. Now let's discuss the first step in detail, which is sampling of analog signal. An analog signal is represented by an expression written as xa of t. A actually denotes, the subscript A is actually denoting it is an analog signal. So xa of t is equal to a cos 2 pi ft plus theta. Here we are representing frequency by capital F. So this is an analog signal, and we can take an example that the plot shown in the slide, as indicated by the pointer, represent this analog signal, and we have to sample this analog signal at discrete values of time, which is the requirement of this sampling stage. So in this discussion, or in this conversion process, we will going to limit our discussion to an specific sampling type, which is basically uniform sampling. We can also do non-uniform sampling, but our scope is limited to the uniform sampling. And uniform sampling is basically the one in which the sample intervals are periodically spaced. You can also see this from the second plot, that the samples are uniformly spaced. The time between the first and the second sample is equal to the time between the second and the third sample. So this type of sampling is called uniform sampling. So in this sampling, what is going to happen? Xa of t, which is the original signal, is converted to x of n, which is the discrete time signal, and we have this relationship due to the uniform sampling. You can also say that by means of uniform sampling, xa of t is equal to xa of n, capital T, which is equal to x of n. So we have a linear relationship between the two variables, which is time and n. Time belongs to the continuous time domain and n belongs to discrete time domain. So we have a relationship known as t is equal to nt, as indicated by the pointer. We got this relationship because we are considering the uniform sampling, that is capital T. So, and you can replace the T by frequency also. You know that time period is inversely proportional to the frequency. So in this expression, we equate nt to n over fs. So here in this expression, capital T is the sampling interval or the sampling period, and fs is the sampling frequency or sampling rate. Recall the term sampling rate. We have discussed this term in the previous slide, that we have to select an appropriate sampling rate for correct sampling. So this fs is basically the sampling rate. So in this way, With the help of uniform sampling, Xa of t, which is an analog signal, can be related to x of n, which is a discrete time signal, and you can relate with the expression x of n is equal to xa of nt is equal to xa of t for any value of n. This relationship is true for any value of n. If you put any value of n and the time period, you will get the same result on both the side of this equation. And by means of block diagram, I am trying to say that if you provide input signal as an analog signal to a sampler block, which is going to perform sampling of this analog signal, you will have a discrete time signal represented by x of n, and this sampler block can be generally represented by a switch, a simple on-off switch. For our understanding, we can say that this sampler is a simple on-off switch, and we provide input, and the switch is going to perform its operation, which is going to on and off at certain time interval, which is the sampling period, or in other words, the specific frequency known as the sampling frequency indicated by f of s in this block. So this switch is going to close or going to open at a rate fs, which is the sampling rate or the sampling frequency. And if this happens, then we will get the samples of our continuous time signal at discrete values of time, which is shown by the plots. If we provide an analog signal like this, we will get, and we select an appropriate sampling rate, then we will get the discrete time signal in result. I hope that my lecture is clear till this point. In this lecture, we have discussed the importance of analog to digital conversion, what is the requirement to convert an analog signal into a digital form, what issues or problem may arise in this conversion process, and how we can overcome them. We have discussed the steps involved in this conversion process and start with the first step, which is sampling, and discuss few points related to this sampling. Now I would like you people to search that what is the sampling rate, or we can say that usually which sampling rate is selected to sample the most popular signals, such as if you want to sample your speech signal, then what rate will you select so that you will obtain an accurate signal. You may also do this task with some other signals related to biomedical field, such as ECG signal or EEG signal. You have to search that what standard is to be followed in selecting the rate or sampling rate of these signals. So this is all about lecture number 7. We will discuss more about sampling with mathematical expressions and more interesting phenomena in the upcoming lecture with the other topic.